Okay, so the next question is an NMR question. So we've got two different structures here, and they mention that the question is to suggest how they could be distinguished from each other from the NMR data. All right, so if we take a look at the first one, diethyl ether. I believe using IUPAC name, this would be ethoxyethane. Anyways, one thing about it is that it has a plane of symmetry. If you were to cut this molecule down the middle, these two carbons right here, along with their hydrogens, would be equivalent to each other, and these two would be equivalent to each other. All right. So there would only be two separate chemical environments, one for these hydrogens here, and one for these hydrogens right here. So taking a look at what this would be right here, these hydrogens right here have this guy as neighbors, so there's three hydrogens coming up here. So this one right here would exist as a quartet. All right. So there would be a quartet. So that would be a quartet. It would have be for a total of 4 hydrogens. 1, 2, 3, 4. All right. And these guys right here would be a triplet, because when you look at this guy right here, it has 2 neighbors to it. So that would make that a triplet. And it would integrate for a total of 6 hydrogens. So trying to predict where the chemical shift for these hydrogens would be right here on A, notice that this is a CH2, which is next, which is bonded to an oxygen. So looking at the data table, it would fall into this category right here, where you've got a CH2 directly bonded to an oxygen. So a good estimate would be that its chemical shift would be about 3.5 ppm. For the chemical shift of B, notice that these hydrogens right here are 1 carbon removed from that oxygen. Right, so they would not be nearly as de-shielded as these are right here. So this would be the best example of that case right there. And on this one right here, where it's got the CH3, it's assumed that this would be some sort of carbon right here. All right, if this was an oxygen right here, it would certainly not be at that same location. So that's why an estimation of 1 ppm would be where you would find this signal right here, which again would be a triplet because of how many neighbors it's got. All right, so for this one right here, drawing it this way, this carbon right here would be a triplet because it's got 2 neighboring hydrogens. This one right here would actually be a sextet, 6 peaks in its signal, because it's got 1, 2, 3, 4, 5 neighbors. So the signal would have 1 more than the number of hydrogens it has as a neighbor. This one right here would be a quintet because it's got 1, 2, 3, 4 as neighbors. All right, and this guy right here would be a triplet because it's only got 1, 2 neighbors. All right. In terms of also there's this one last one right here. This guy right here, OHs, alcohol hydrogens, tend to be broad singlets. All right. So in terms of figuring out where things are, this guy right here would be a fairly de-shielded signal because it's directly connected to that oxygen. All right, and using the data table, you can see that it would appear around 3.5. All right, this would be the most shielded. All right, so there's nothing really that's going to pull the hydrogens away from, or any of the electron density away from these hydrogens. So that's why that one would be expected to be around 1.0. All right, and these CH2s in the middle would be about, you would expect to see them about 1.4. They would probably end up overlapping with each other so that you would not be able to tell a sextet versus and a quintet, because when those signals, when they're separate, you can see what they are, but when they start to overlap, it just starts to get really messy. So in terms of how you would distinguish, there's several things you could say. You would only expect to see 2 signals in this one, whereas you'd see 5 total signals here. You could mention some things about the splitting patterns that, for example, you've got one, like for here, you'd have you'd expect to see a broad singlet here because of the OH, where you would not see any broad singlets here. If you just mention the types of splittings that you would see for these, that would also be acceptable. All right, but one of the biggest things that you would stand out to you the most would just be the number of signals. All right, this is a symmetrical molecule, so you'd only see 2 signals for the 2 different chemical environments, whereas we've got 1, 2, 3, 4, 5 different chemical environments, which would give 5 total signals. All right, so how can we tell the difference between using IR? And one thing about IR is to focus on things that are strong signals. Okay, so a lot of times the difference between molecules might be whether or not they have, for example, an OH group. An alcohol would have an OH stretch in it, but something that doesn't have an alcohol wouldn't. All right. Also, this carbonyl stretch right here would be very diagnostic. All right. So focus when you're looking at the IR data. It's probably a good idea to focus on the things that are considered strong signals. All right. And OHs in either, say, for example, a carboxylic acid or an alcohol would be examples of things to focus on. All right. So when looking at these two structures, right here, one thing that you would should stand out is you would expect to see that strong OH stretch in the alcohol, but there isn't an OH bond in this molecule right here. All right. So the difference would be the presence of that strong broad OH stretch at about 3,400 inverse centimeters, whereas this right here, you would say the absence of that stretch. So in the last question, it just says draw 3 resonance forms with the curly arrows showing the electron movement of a sulfate ion. All right, so first of all, figuring out the Lewis, let's start off with an acceptable Lewis structure. All right, so we start with sulfate. Let's count the number of valence electrons. We've got 6 for sulfur, 6 for each of the oxygens. And then we're going to get 2 extra valence electrons because of the charge here. That makes a total of 32 valence electrons. So let's start just by putting a central atom in the middle, connecting everything with single bonds. At this point, we would have 2, 4, 6, 8 total valence electrons. All right, so that means that we've got to add a total of 24 to get up to that total of 32. All right, so if I put 6 of them, three pairs around each of the oxygens, we could draw a Lewis structure like this. Notice that puts a formal negative charge on each of the oxygen atoms with a positive 2 charge on that sulfur. All right. So remember, we want to share electrons to accomplish mainly 2 things. First of all, we don't want to have any atom having anything other than a -1, 0, or positive 1 charge. All right. Notice we've got a positive 2 charge. You're generally not going to want to have that in a Lewis structure. All right. Also, we want to try to eliminate as much as possible having a positive charge on one atom with a negative charge on a neighbor. All right. So one quick way to do that is if we bring these electrons in right here, bring these electrons in right here, and that would create this structure right here. All right. Notice we've gotten rid of both of these problems right here from this originally drawn Lewis structure. All right, so this would definitely be preferred over this. All right, so using that preferred structure, we can draw some resonance forms. All right, I could take these electrons, move them in, take these electrons, put them up on the oxygen. That would give this structure right here. Don't forget to put your negative charges on the oxygens to indicate their charges. Then I could move these electrons here, put these ones up, and we could get this structure right here. We could keep on, there's several more of these that we could do. We could move these electrons down here, see, and move these right here up onto this oxygen, and just make sure that what you draw doesn't repeat something that you've already done. All right.